So good morning, everyone. I'm Angela, and thank you, Crescenzo. Thank you to the Astromeeting committee for giving me this opportunity to talk about my PhD thesis once again. So the title of my thesis is The Fate of Late-Type Galaxies in the Fornax Cluster, Mapped with Deep Imaging Data. In today's talk, I'll give a brief introduction, or rather a scientific background of the work that was undertaken in my thesis, the data I used, methodology, the main results of this work, the discussion, conclusions, and future perspectives. So I always like to start with the morphology density relation by Dressler in 1980, which says that the spiral to elliptical ratio is often lower in clusters than the field. In this diagram here, we see that the fraction of spiral galaxies decreases with increasing projected density, while that of elliptical galaxies increases with increasing projected density. Now, this suggests that the morphology of a galaxy depends on its environment, such that high-density regions inhibit the formation of spirals. So over the past years, there have been dedicated works to understanding this, and the questions are, how do spiral galaxies evolve in dense environments, whether it's through disk fading, spiral merging, or that spirals experiencing harassment can also resemble a lenticular. We're also asking if we can actually trace the evolutionary path of spiral galaxies and predict their fate. So keeping these in mind, my thesis focused on the study of late-type galaxies in the Fornax cluster, which comprises the cluster core and the infalling group. We used deep imaging data and some ancillary data to study the effect of the environment and the evolution of its constituent late-type galaxies, thereafter predicting their fate in the Fornax cluster. So small fluctuations in the hot universe created the first seeds of galaxies, which has since been supported by the lambda cold-up matter model of galaxy formation. And this image here, we see simulations of millions of galaxies in clusters and superclusters forming the galactic filament. And what is galaxy morphology? So it's a product of the formation and evolution of a galaxy and characterizes it based on its interaction with the environment, its structure, star formation history. And of course, there are several classification schemes. And among them, I'll just define what the Hubble stage T parameter by D booklet is, as I will mention it in today's presentation. It's a parameter ranging from -6 to +10. On the left side here, we have early-type galaxies. On the right, we have late-type galaxies, which are spirals and irregulars. Now, later classification schemes also included dwarf, specular, and central dominant galaxies, some of which I mention in today's presentation. The question is, why late-type galaxies? And first of all, the spiral arms of these galaxies are the birthplace of stars. I like to call them the cradle of structure formation because of the presence of bars, thick and boxy disks. Additionally, the transformation of these galaxies into lenticular systems will a debate, whether it's through hierarchical merging, a suppression of their star formation as a consequence of the dense environment in clusters. Speaking of dense environments, what are the mechanisms that transform galaxy morphology here? So here are some of the famous processes taking place in dense environments. And among them, I'll just briefly describe what strangulation is, as I will use it in today's presentation. So it's a process where the hot to warm gas of a galaxy is stripped, preventing further inflow of cold gas, eventually halting star formation and transforming the galaxy morphology here. So sometimes galaxies part of groups can also undergo this transformation before cluster and fall, otherwise known as pre-processing. So where do we investigate these phenomena? So here we have a supercluster, the Fornax Eridanus complex, hosting several clusters and groups, such as the Eridanus subcluster in the north, Dorada group in the south, and we have the Fornax cluster, which has the highest mass concentration in this region. So white Fornax. It's a second nearest cluster with mass assembly still ongoing. Here is an image to help with visualization of this cluster. It's one part of the cluster core here. There are many early type galaxies. There are some famous late type galaxies like NGC 1365. We also get to look at the Fornax A group. So it's a supposedly infalling subgroup. Just to remind you where this group is, so there's an infalling group here. It's a region of intense star formation. And from this image here, we see it's dominated by bright late type galaxies. So we get to look at two different environments at the cluster core as well as an infalling group. And this cluster has a wealth of data. So there are several surveys which have investigated or currently studying this cluster. And the work presented in my thesis is based on data from the Fornax Deep Survey with VST. I also used Edge Alpha data to give an idea of the star formation activity in the Fornax A group. We've used results from the ALMA Fornax cluster survey on molecular gas, mu spectroscopy, and MeetCat survey on atomic gas. Before we go into details about the Fornax Deep Survey, it's important to know the need for deep imaging. So the imprints of mass assembly reside in the outskirts of galaxies and dense environments extending out to about hundreds of kiloparsecs. It's in these regions where the stellar halo and structures such as the tidal tails, shells are found. Now, to show the importance of depth, we have an example here. And on the bottom right panel, we see that with greater depth, we're able to look at the faint outskirts. So what's the need to look at or study this region? We get to study regions such as the tidal streams, which can last for several giga-years and serve as a fossil record of the formation history of a galaxy. We also get to study features like truncations and disk breaks, and the intracluster intragroup light. So what is a truncation? It's a decline in the surface brightness profile of a spiral galaxy, and disk breaks are quite the same. So I would say type 2 downbending break is about the same as a truncation, just that truncations are observed or detected at lower surface brightness levels. So we have three types here. Type 1 is a no break, type 2 a downbending, and type 3 an upbending break. As part of the work in my thesis, I developed an algorithm to detect this feature, and I will explain that in some time. Now, these two features can coexist, but their origin can be of different phenomenon. Next is the intracluster and intragroup light. So low velocity dispersion in group environments favors processes like interactions and merging, which result in the formation of tidal tails and plumes, as well as stars expelled into the environment. So this constitutes the intragroup light. Now, as these groups merge to form the cluster, more processes increase in dense environments, gradually increasing the intracluster baryons. This is important to study as it gives us information about the assembly history of the cluster or group. It's only possible to detect with deep imaging due to their low surface brightness, as well as wide field images are required to map this component, which extends to about 100 kiloparsecs in clusters and groups. So here's an example of the intracluster baryons detected in the core of the Fornax cluster. So to do this, we need wide field images and deep imaging data. And that's where the Fornax Deep Survey with VST comes in. It's a multi-imaging survey of the Fornax cluster, and previously the survey has been able to map the light distribution out to 15 times effective radius, as well as down to 20 to 30 magnitude per arcsecond square in surface brightness. So the survey deals with several topics concerning different aspects of galaxy evolution, and among them, my contribution is to the study of late type galaxies in the cluster core, as well as the study of the Fornax A group, in particular, the bright galaxies and intragroup light. So what's the motivation of this work? Or what are the key questions I'd like to answer through my work? So first of all, we're looking at two different environments, the cluster core and the infalling group. The questions are, how different are the structures of late-type galaxies in these two environments? What about their structural parameters and observational properties? How different is the break radius and break type? What does the ICL or IGL have to indicate in the context of the assembly history of the cluster itself? The lambda CDM paradigm, how does the IGL contribute to the ICL? And how is this helping us understand pre-processing and the hierarchical merging of groups onto the main cluster? With all of this information, can we trace the evolutionary path of the cluster core late-type galaxies and predict their fate? So we'll answer all of these questions in the discussion part of today's talk. Moving on, I will briefly describe the Fornax deep survey data, the sample, and the algorithm used to detect disk breaks. So the Fornax deep survey observes 26 square degrees of the Fornax cluster. We have the Fornax score centered on NGC 1399 and the Fornax Southwest group centered on 1316. So the real radius is indicated in both cases here. And among the several giant galaxies, my thesis focused on the study of late-type galaxies, which are 13 of them in the core and 9 of them in the subgroup, making a total of 22 late-type galaxies brighter than 16 magnitude in the Fornax cluster. So here we have the algorithm to detect disk breaks, and this is a surface brightness profile of one of the galaxies in the sample. It's fitted with a single exponential. The green bar here indicates the model, the RMS of the model, and this suggests the presence of wiggles in the profile, or it requires a second exponential fitting. Well, I think it requires a second exponential, and the break radius is probably around 70 to 80 arcseconds here. So the algorithm works on basic principles, and the idea is that it fits two exponentials, one in the upper disk and lower disk, by varying the region over the entire disk. And for that, each of these variations, an intersecting point is estimated. And for several combinations, a sigma, a standard deviation of the several intersecting points, is estimated. Again, here, the green bars indicate the RMS of the model for the upper disk and lower disk. So you'll observe that on iterating this step, as the fitting gets better, the red bar on the top, that's a sigma, also decreases. And finally, the one with the minimal standard deviation is the break radius, which is around 73 arcseconds. So now that we have the data and methodology ready, we can move on to the results. I will just talk about the main results of this work in 3 parts. First, about the galaxies in the core of the Fornax cluster, then the Fornax A group, and then the intragroup light in the Fornax A group. So we have 13 LTGs brighter than 16 magnitude inside a virial radius of 0.7 megaparsec, the Fornax cluster. And here we're going to just answer the main questions. These are, if there is a morphology and color segregation, what about the disk breaks and break type? So yes, we do find a morphology segregation. This is a Hubble stage T parameter I mentioned earlier on the y-axis, and projected distance from the cluster center on the x-axis. So we have early type galaxies, triangles and circles are late type galaxies. And from this, we see that the late type galaxies, the very late ones, are located beyond the high density ETG dominated regions of the cluster. To support this, we also have the stellar mass versus projected distance. And we see that there's a clear segregation of the late type galaxies from the bright ETGs here. So what about the disk breaks? Now, 10 out of 13 galaxies exhibit a disk break in their profile. And I'm just going to show a few examples. So here we have images, G-band images and surface brightness level of 2 galaxies. This is FCC 263, a bright spiral galaxy, and we have FCC 179, a spiral galaxy. In both cases, the break radius is indicated, so we have the black dashed lines. And this FCC 179 is a type 2, so this is the same profile I showed earlier in the algorithm, and the G-I color is also indicated here. So we used the molecular gas contours from the Fornax cluster survey. So we overplotted them, and we see that, or we find that the detection is within the break radius for these two galaxies. So the contour is here. So a few more examples. We have a spiral galaxy and the famous 1365 Watt spiral. Now this galaxy shows a type 3 plus type 2, so that's an upbending profile and a downbedding on the outskirts. Again, zooming in, so we see that the molecular gas detection is within the break radius. So some more examples. So here we have tidal tails in the case of FCC 312, and in the case of 306. So zooming in, we see that the molecular gas detection is within the break radius. So this is a plot of the magnitude versus break radius normalized to effective radius. And the colors here, blue and red, indicates that it's the outer disk minus inner disk. So blue would mean that the outer disks are blue, and red the contrary. So here we find that the galaxies, the break radius of these galaxies of 80% of the sample are located within one effective radius. So just to summarize the main results of this part of the work, 10 galaxies show disk breaks. Molecular gas detection is within the break radius. Doesn't have to be a cause effect though. The break radius is within one effective radius, and we find a clear morphology segregation. That is, the very late TEP galaxies are located beyond the high density ETG dominated regions. So what about late TEP galaxies in the Fornax A group? So here's an image of the Fornax A group with all the galaxies, part of the group marked here. The blue circles are the giant late TEP galaxies, which are 9 of them. The red circle here is the virial radius, and the black circle is the region within which we estimate the intragroup light. Now to compare this with the cluster core, we have to ask the same questions again. That's about the morphology and color segregation, about the disk breaks and break type, as well as the assembly history of the galaxies in the group. So we don't find a morphology and color segregation. So here, there's only one ETG, that's the central dominant peculiar galaxy in GC 1316. The remaining are bright late TEP galaxies. There is the stellar mass and effective radius correlations with the cluster center and group center. And we don't find any correlations or segregation of any sort. So let's look at the disk break. So 6 out of 9 galaxies exhibit a type 3. That's an upbending profile in the group. So again, just to show some examples, here we have 3 of them. The break radius is indicated. What you'll see is that the break radius is located beyond one effective radius for 6 of these galaxies in the group, unlike what was observed for those galaxies in the cluster core. So it's the contrary. So we have orange triangles and green circles here, which was within one effective radius. So let's look at the assembly history. We take spectroscopic redshift from Maddox and collaborators, and we study the assembly history via projected phase space explained by Rhee and collaborators. So according to this diagram, the y-axis is the velocity of galaxies normalized to the central velocity dispersion. On the x-axis, we have the radius normalized to the projected distance normalized to the virial radius. The blue trajectory here is the escape velocity, and according to Rhee and collaborators, galaxies on infall will remain close to this curve here, and as they start to gain velocities, they move towards the region of recent infallers, and after passing through many apocenters and pericenters, they reach the region of the intermediate infallers, and finally, ancient infallers here. So from this diagram, we see that most of the group members are intermediate and recent infallers. I've put the same information from the PPS and the types on this image here to help with visualizations. To summarize our results, the main results, 6 galaxies with disk break, and break radius is located beyond one effective radius. We did not find a morphology and color segregation, and most of the galaxies are recent and intermediate infallers, except for these two here. That's 1317, his morphology resembles that of a lenticular, and 1316, that's the central dominant galaxy. So it looks like the cluster core is at a different stage of assembly compared to the infalling group. So what about its intragroup blade? So we estimate the intragroup light in this region here. What we do is that we model the stars and bright galaxies, subtract them from the image. We're left with these faint structures of 1316, and we estimate the intragroup light here. So to understand the buildup of the IGL, it's important to know the formation history of 1316. That is happened between through a merger between a dominant gas-poor ETG and a smaller gas-rich spiral galaxy. These famous loops are also shown here, just to remind you where it is. And within that circle here, this region, Vennola and collaborators found a significant drop in the number of dwarf galaxies, which also contributes to the extended stellar envelope. So now that we have an idea of the formation history of NGC 1316, we can study or understand the buildup of the IGL. And this is done through comparing our observations to predictions from models. From observations, we have the fraction of the IGL luminosity to the total luminosity of all group members inside the group, which is 16%. And then we have two models here. So we have the merger channel and the accreted channel. So here we have other groups too plotted. And the black one here is 1316, and it kind of fits in. So to summarize, the buildup of the IGL from this is that through a past merger of 1316 and disruption of satellite galaxies in infall. So our observations fit in well with predictions from models. And now that we have our results together, we can answer the key open questions I asked earlier. I'll do this in 4 parts. I'll first talk about the difference between the cluster core environment and the infalling group, then the hierarchical merging of groups in the main cluster, about pre-processing, and finally predict the fate of late-type galaxies in the Fornax cluster. So the first question was, how different are the structures of late-type galaxies in these environments? So here we have the projected phase space obtained from Fornax 3D. And just to show a few examples, so we have tidal tails in the case of 312 and 306 here, and then we have lopsidedness in the case of FCC 285. So what we see is that the LTGs in the core show more irregularities in your structures in comparison to those in the group, which had more regular morphology. Additionally, we do not find morphology and color segregation for those galaxies in the Fornax group, like what we found for the cluster core galaxies. Here we see there's just one ETG and there are several early type galaxies here, suggesting that the environment is more evolved. To look at some observational properties and structural parameters, so we have the projected phase space information again. And additionally, there is some information about the star formation activity here. I've done the same for the Fornax A group, and here it is from H-alpha data. So here we have 2 galaxies, that's ancient infallers, and the remaining have high star formation. So unlike what was observed in the cluster core. So also there's the X-ray distribution here, which is much more extended, and the luminosity is also higher than the group, which is in this case only because of 1316's merger history. So about the dysboric SEM break type, in the cluster core we detected type 2 and type 3 dysborics. In the subgroup, there are only type 3 bending profiles. In the cluster core, the breaks could indicate a component transition. They were detected at the edge of the spiral arms beyond which there was no molecular gas or star-forming regions. And in the group, these type 3 breaks could either indicate strangulation or H1 richness. Now, both of these processes are contradicting, and hence H1 data is required to confirm them. And we also saw that the break radius of the type 3 galaxies in subgroup were located beyond one effective radius, contrary to what was observed for those galaxies in the cluster core, which is within one effective radius. So the cluster core LTGs are undergoing a significant transformation in the morphology, beyond where we don't find these star-forming regions beyond the break radius, there's no molecular gas, and some of these galaxies also resemble lenticular systems. And the galaxies in this subgroup are mostly young, and suggesting that the environment is at an early stage of assembly with respect to the cluster core. So what does the ICL or IGL have to indicate in this context? So here we have the same diagram from before, and the orange dots here are the west-northwest clump. The bulk of the ICL is from this region here. So this is a group of galaxies which assembled during the cluster collapse. And the fraction of the ICL in the cluster is 34%, and we find the IGL in the group to be 16%. So the low fraction of the IGL is indicating that the processes are not, much to have contributed to the intra-cluster baryons detected there, unlike what is observed in the cluster core. So it therefore supports that the Fornax A group is in an early stage of assembly. The lambda CDM paradigm, how does the IGL contribute to the ICL? So in the cluster, there are 3 well-defined groups. That's the core, the north-south clump, and the infalling galaxies. So during the process of infall, here in this case, the IGL mixes with the ICL. So like how the bulk of the ICL is from this clump of galaxies. So the processes that happen in the low velocity dispersion of galaxies in groups contribute to the intragroup light, and then this mixes with the intracluster baryons. So speaking of pre-processing, let's see if any of our galaxies has undergone pre-processing. So here is FCC 179. It's a recent infaller and has low star formation. Additionally, this galaxy has the break radius located beyond one effective radius. So we have clues from phase space at the recent infaller. There's the break radius located beyond one effective radius. It has low star formation rate. There's no H1 detection. And the morphology of this galaxy resembles that of a lenticular. So the question is if this galaxy has undergone pre-processing. The answer is yes. It was part of a group that recently assembled into the cluster core. So we've looked at those galaxies which are pre-processed, and those which are undergoing transformation in the cluster environment. And putting all of this together, we can try to predict the fate of LTGs in the Fornax cluster. To do this, we have to compare results from observations and to simulations. So from observations, we have deep imaging data. We look at the faint features, the morphology, the cluster-centric relations, disk breaks, observational properties, as well as phase space analysis. So here's an example. So we have FCC 176, which is an ancient infaller. It is devoid of gas, resembles a lenticular, with morphology of an early Barth spiral. So it looks like this galaxy has spent the most amount of time in the cluster and undergone the largest change in morphology. From simulations, we look at the number of pericentric passages, the current distance to the cluster center, and pre-processing. So here we have cluster disk galaxies that spend longest time in the cluster experience the largest change in morphology, like in the case of FCC 176. So pre-processing is important to look at here because galaxies in the cluster can have different accretion times. And this also gives us an idea about how many groups have assembled into the cluster core. And to this work, we have I've looked at each of these galaxies individually, studied their structure and evolution, put them together to understand the effect of the environment on their evolution in the cluster. We've seen the need for deep imaging, as well as comparing this to multiple wavelength data. Within Fornax, we've seen how different the impact is on the structure transformation of constituent galaxies, making it one of the most preferred regions in the local universe to test out theories concerning the evolution of galaxies from the biggest to the faintest. The novelty of this work is that we have a new approach to understanding galaxy evolution in dense environments. That is, via the algorithm to detect disk breaks, which is a good indicator of structure transformation, and comparing this information to other observational properties. We have explained the physics of mass assembly in large-scale structures. The densest parts of these large-scale structures are groups and clusters, and through this work, we've shown how different the impact of the environment is on the cluster galaxies and the unfolding group galaxies. And all of this has been made possible with new deep imaging data from the Fornax Deep Survey. So future work would be that we would look at explore the outskirts of clusters where the unfold and realization of matter take place, like in superclusters. An example would be the Fornax Eridanus complex. To study disk breaks in different environments and across cosmic time, determine the nature and cause of truncations and disk breaks of galaxies in clusters and groups, and connect these properties and features of galaxies with a proposed mechanism to further understand pre-processing of galaxies as well as hierarchical merging of groups. And thank you for your attention.